Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a new concept of flow of viscous fluid between two parallel plates. In our previous lecture, already we have discussed the flow of viscous fluid between a circular tube or in a circular tube. So here it is different. We have taken two different parallel plates and which are fixed. So this is a parallel plate and this is another one parallel. This is another one plate. So both are parallel to each other. This is one plate, plate 1, plate 2, and both are parallel to each other. And the direction of fluid, you can see arrow marks are given here. So this is the direction of force. Now in the similar concept, in this topic also, we are going to derive few terms, or we are going to discuss few terms like last class or last video what we have discussed, that velocity distribution is there. Okay, and second we have discussed about the velocity distribution across the section and the ratio of maximum velocity to the average velocity. So this also we have discussed, maximum velocity to average velocity. And apart from that also we have discussed the shear stress distribution. So that also we need to derive in this. And another one is pressure drop. Another one is pressure drop in a given length. And the next is our fourth one is shear stress one. So these are the things we are going to discuss or we are going to derive in this topic. So similarly, again we have taken a concept of this viscous fluid. So there is two different plates are there which are parallel to each other, and a viscous fluid is flowing through this. And to get this concept of this, to derive this concept, we have taken a small element in this, and that element here it is ABCD element we have taken here, and the fluid supposed to be flows from the left to right edge, from this side to this side. So this is our left side and this is our right side, and these two plates are situated with a height of, or with the thickness of T. Okay, so the length of this here, if you see the length of this element or the fluid element what we have considered here, so that is delta x. Okay, so these are the data I supposed to inform you. So these things we have considered, and the fluid element also is situated with a height of y from this base, or from this plate 1 or plate 2, whatever you can consider. And this plate, this fluid element is having a thickness of delta y. Okay, and one more thing, this plate, like this fluid element, it's looking like this, but this fluid element also can be drawn in this way. Okay, which is having a this kind of shape will be there, suppose. Okay, so in that condition we need to consider the thickness of this fluid element. Okay, what is the length of that and height, as well as the width of this, or the width or thickness, whatever you can consider in this way. Okay, so now when it is flowing, when the viscous fluid is flowing through these two parallel plates, okay, so there are certain forces are acting on this fluid element. Okay, so what are the forces are going to act on this fluid element? As we know that there will be a pressure force which is going to act on this surface in this face AB, and another one pressure force which is going to act on the CD face. Similarly, AD surface or AD face, one more force is going to act, and BC, one more force is going to act. So here what I meant to say, all these faces, there are some forces are going to impact on the all sides. So what are the forces are going to impact? Now first one I can say the pressure force on the side, on the face AB. Okay, and similarly pressure force on the face CD. You can see here this is AB and this is CD. So here one pressure force is going to act, and another side another pressure force is going to act. Already this concept we have discussed previously many times, still I'm telling. So when you are going to calculate the pressure force in this, we know that force equal to, or you can say pressure equal to force by area. So we can write force equal to pressure into area. So what is the pressure at this particular moment? Okay, that into the area need to be considered. Okay, so here pressure we don't know, but we need to write what is the pressure force is going to act on this. So I can write the pressure force on the AB face is nothing but the pressure P is going to act on this, and the area, so area we can say this is the height of that object and the width of this object is nothing but 1 we can consider. So this is P delta Y into 1. Okay, similarly in the reverse side, if you see in the reverse side CD, there is a reverse force is going to act on that, and which will be opposite to this force. Okay, then only we can say it is in equilibrium condition. And what is the force is going to, or what is the pressure force is going to act on the CD surface? So what pressure already acted on that particular point, and still again some portion is covered here. Suppose this is the, here there is a P applied here, or pressure which is applied here at this particular area. So if you see at the other end, okay, the same pressure is not going to be there. Some changes in pressure will be there, because the pressure which is acted here, if you divide, because it's covering some distance, see it's covering some distance here. So what is the distance is there? Delta X. So each pressure or each zone, some pressure is also acting on that. So each zone, how much is there? Suppose I can say, now I can say each distance is suppose delta P with respect to delta X. That means each zone there is a pressure is acting, and what is the distance of that? Now delta X. So this is the pressure gradient what we have considered here, delta P by delta X. So similarly delta P by delta X, delta P by delta X, delta P by delta X. So multiple number of delta P by delta X is there. That means total distance how much covered? Delta X. So what we can write, the pressure what is applied here along with this total pressure which is acting on this particular element, okay, with respect to the area. So the total pressure is going to be P plus, I'm writing only pressure, P plus delta P by delta X, the pressure gradient. How much distance is covering? The total delta X. So I can write this is here delta X. So this is your total pressure which is acting at the opposite side, CD surface, and this is only pressure. What about the area? So area also I can similarly write delta Y into 1. So these things already we have discussed in previous videos, so you can refer to that one also. So these two are pressure forces. Similarly, at the two other surfaces or two other phase, okay, there is a shear force is going to act on this, because it is in fluid is moving condition. So there is a shear force is going to act by this surface. Okay, so what are the shear force is going to act here? Now here also similar thing, shear force on the BC face, on the face BC. This is the BC face. So the shear force also is going to be act on this in this direction. Okay, is going to be act in this direction. It is reverse to this one. Okay, so what will be the forces here? Shear force. So I can write tau. Tau is the shear stress. So again here also similar thing, stress equal to the force by area. So here if you write the shear force, so stress into area. So shear stress is tau. Again we need to consider the area. So area is how much length is there, what the length along with the width. So length is delta X and width is 1. This is the shear force on the BC surface. And similarly the shear force on the AD. On the AD if you see, this is the shear force is there, and there we can write this is at this particular point. Okay, so this shear force or this shear stress is covering again the total height of this. Okay, so similarly if you see each shear stress is going to cover from here to here, so again it's going to be increased similarly. So I can write again shear force at the other surface, that is AD. Also I can write tau, the initial shear stress which is applied, it is plus the delta tau by y, delta y, because the delta y is the height is there, and each zone, suppose delta tau is there, so I can write delta tau, the small shear stress which is applied, and with respect to y distance covered, and how much with respect to delta y and into del y into delta y here. Okay, this is only shear stress. What about the area? Area you can write delta x into 1. So this is all about the forces which is acting on this fluid element along the all the surfaces, all the sides. Okay, so again one more thing, for steady and uniform flow we can consider there is no acceleration is there. Okay, so the resultant force in the direction we can write to be 0, and that means the summation of force equal to 0 we can say, or we can say the forward direction force and reverse direction force, the summation is supposed to be 0. So or else we can write, implies what are the forces is there. So first one, P delta y into 1 thing you can write, and minus, because the reverse one this one, so directly I'll write this value P delta y, and this is minus del P by del x into delta x delta y, 1 I'm not writing, again minus of tau dx, tau delta x into 1, and this is plus, we can consider this is plus direction is there, so that is tau delta x plus delta tau by delta del y into delta x equal to 0. Okay, now if you cancel these things, so this part is going to be cancelled, and remaining part also we can see tau del x also is going to be cancelled here. So remaining terms we can write here minus del P by del x delta x into delta y, plus here also same, plus del tau by del y delta x into delta y equal to 0. Now we can just segregate this, or we can divide delta x delta y, so that we'll get, finally we can write this equation del P by del x equal to del tau by del y. So this is very simple, and this one we can give a equation 1. Okay, this one you can give a equation. Now these things very easy, you can understand. I have just taken one side, one value in the right hand side, and both minus will be cancelled, and after that I just cancel del x delta x delta y in both sides, or else you can do dividing the delta x delta y, here delta x delta y, here delta x delta y, then we can be cancelled. So what will get, minus del P by del x equal to minus del tau by del y, minus minus cancelled, so del P by del x equal to del tau by del y. Okay, now we will start this derivations. Okay, first one you can see velocity distribution. So the velocity distribution in the two different plates, or two parallel plates what we have taken here. So to obtain this velocity distribution along the section, okay, the value of shear stress need to be considered. So the value of shear stress, we know that tau equal to mu into du by dy. So this equation already we have discussed in the previous video, along in the starting lecture also, while discussing the Newton's law of viscosity. That time also we have discussed this. So this equation need to be considered, okay, viscosity for the laminar flow. And now what I'll do, I'll just put this value in this equation. Okay, so if I'll put this value in that equation, then what we'll get, now del P by del x equal to del of tau is there, So mu into what will get? Del square u. Okay, let me write directly mu into del square u by del y square. Okay, or we can write this del square u by del y square equal to 1 by mu del p by del x. Okay, now what I'll do, this equation I'll just integrate with respect to y. This equation I'll just integrate with respect to y. If I integrate this equation with respect to y, then what will there? I can get here del u by del y, and here 1 by mu will be constant, we can take it out. So 1 by mu, and this is del p by del x, as usual will be there, del p by del x, and here is a constant term what we have taken outside, and with respect to y we have considered, so here y plus, here you can write c1. C1 is the constant. Okay, now see what we have just integrated this one, and del square u by del y square equal to 1 by mu del p by del x. So this integration what we got here. Okay, now again one more integration will do here. Integration. Why I'm doing the multiple integration? Because I want to convert this equation in terms of u, a simple terms. So integration of this again will get u, and this is already 1 by mu, we can take it out, 1 by mu, and del p by del x, y is there, so integration of y again we'll get here del p by del x can be taken out as a constant, and y integration will get y square by 2, so y square by 2 plus this c1 integration that we can write c1 y plus again one integration c2. So these are the constant of integration are there. So now you can give this equation 2. Okay, now this c1 and c2, as I told you, that this is the constant of integration, c1 and c2. So for this also boundary condition is there. Now as I told you, the c1 and c2 are the constant integration. These values, their values will be obtained from the two boundary conditions. So first boundary condition we can consider at y equal to 0. At y equal to 0, what will be there? You can see, yeah, for this I'll draw one diagram, velocity profile I'll draw. Here if you see, as the liquid is flowing, okay, through this parallel plate, okay, we can see at this boundary, at this surface of this boundary, okay, we can see there is no movement of the fluid, or the fluid movement is very negligible due to the viscosity of the fluid, and due to that there is a friction also there, and due to that the velocity is at this boundary layer, at this boundary point will be considered the 0. That's why if you see maximum velocity profile or the maximum velocity can be obtained at the center of the plate. Okay, whether it is a pipe or plate, there is always the maximum velocity will be obtained at the center of that flow. Okay, so at this point we'll get 0. So y equal to 0 means at this point, so your velocity also will be 0. And second one I can consider at y equal to t. At y equal to t, that means the total distance what is covered. Okay, in the diagram already I have mentioned here. So here also I can consider again the value of velocity will be also 0. That means at this point. If it was at the middle point, then it is a maximum we can consider, but it is here. Okay, so now what we'll do, just substitute this value in this previous equation. What equation? This equation what we got, equation number 2. Just put the value in this equation. Now finally what we'll get? 0 plus 0, again this c1 into 0, and plus c2. So that means the value of C2 we are going to get 0 here. And again put the value of y equal to t again in this equation. So this is first one. Again just put the value of y equal to t. Here I can write y equal to 0 and u equal to 0. First one. Second condition, y equal to t I can give, and again u will be 0. So again that equation will be here 0 and 1 by mu, and we can write del p by del x, because here the value is, if you see the equation, y square by 2 is there. So now y equal to t, so that's why you can write t square by 2 and plus c1 t plus the value c2 equal to 0 you can consider here. Now this is the equation of that. So what I'll do here, I'll just take the value of c1. So c1 equal to, I can write here minus 1 by mu del p by del x, and this is t square by 2t, because here c1 was there, c1t was there. Now we have taken all these terms to the this part. Suppose if you keep here, and this part will be on this other side, so minus is there, and this t is going to be divided at the other end, so that is 2t. Okay, now if you cancel this, we will get 1 by 2 mu del p by del x into t. T square is there, t is there, so that is cancelled here. So now what we'll do, this is c1 value, this is c2 value. Now this c1 and c2 value put in the equation 2, this equation 2. So what you are going to get after putting the value of c1 and c2 in this, we are going to get u equal to 1 by 2 mu. Yeah, 1 by mu is there. So finally what we are going to get, that I'm writing here after applying. Okay, let's write 1 by 2 mu. This is del p by del x y square plus y into minus 1 by 2 mu del p by del x into t. Okay, and c2 is 0, so no problem. So this was 1 by 2 mu del p by del x y square. Okay, c1 2. So yeah, so this is the value. If you again write this, we can get it by 1 by 2 mu del p by del x. Just I'm taking commons, 1 by 2 mu. This is 2 mu del p by del x. Here it is y square is there, here only y is there, and ty is there, not y, ty. So we can write here ty minus y square. This one you can give equation 3. So if you see this equation, u equal to 1 by minus of 1 by 2 mu del p by del x ty in minus y square. So we know this is the constant term. 1 by 2 mu is the constant term. This is the del p by del x is also constant term, and here t also constant. So what are the various things is there now? Y square. Okay, so that means the u term, okay, the u term is varying with respect to square of y, so that this equation we can say is a of parabola equation, is the equation of parabola. So the velocity distribution, this velocity distribution what I already drawn, okay, from this it is proved that this velocity distribution is going to be a parabolic. Okay, for the two different parallel plates, the velocity distribution is going to be parabolic. Okay, again one more distribution is there, CST distribution, that I'll tell you later. So this is about the velocity distribution. So the next part, what I told you that we are going to discuss, that the ratio of maximum velocity to the average velocity. Okay, as I told you previously, what we have discussed for the circular pipe, same thing we are going to discuss here also. So the second part is the ratio of maximum velocity to average velocity. Okay, so now let's go over take this point. So this one, the first one we have covered here, this first point, velocity distribution, and this is the second point, the ratio of maximum velocity to average velocity. Yeah, now for this we can say the velocity is maximum when y equal to t by 2. When y equal to t by 2, we can say the velocity maximum, because if you see, this is the velocity profile at this 0, 0, and here it is maximum. So if you take half of this is the thickness, so half of this we can get the maximum velocity. So same thing I've written, when the y equal to, or we can say this value distance height is t by 2, this one. Okay, if you see the y value here, this is the y value. Okay, so when it is going to maximum, now when it is y equal to t by 2, means up to here, then we can get the maximum velocity. So just put the value here, and we can write u maximum equal to just the previous equation, what we can write, minus 1 by 2 mu del p by del x into t by 2 minus y square. So that is t by t square, bracket close. Just I will just put the value y equal to t by 2. Okay, so that we can say it is a maximum. Here is only u is there. Now I'm writing u max, and I'm putting the value of y equal to t by 2. So now if you solve this, we can get it. So here we can write 1 by 2 mu del p by del x, and this is t square by 2 minus t square by 4. Just you LHS, RHS we can solve it, and we can get it t square by 4. And again we can write this as a minus 1 by 2 mu, not 2 mu, 8 mu del p by del x into t square. So this is about our u max, the maximum velocity. So this one again, what I can do, I can write equation 4. This is all about the maximum velocity. Okay, now to find out the average velocity, again we can consider this is average velocity u bar, and that will be obtained by dividing the discharge, across the section of the area. What is the discharge of this fluid from here, and what are the area is there, so of the section. So we know that already from the continuity equation, q equal to, I know that I can write q equal to av. Okay, velocity at a distance of y, and what is the area of the strip. So this one we can write here. Again, I'm not able to write this q total, so I can write only dq equal to, I can write velocity at a distance of y, that means this one, this value. So let's write the velocity equal to what, now minus 1 by 2 mu del p by del x, bracket start, t into y minus y square. So this is about the what, velocity. And what about the thickness, area of that area, we can write dy into 1. I'm taking the small one. Okay, only the small distance I'm taking about the element one, then I'll go for the total one. Okay, Now this also I can go for integration of this. Now it is coming integration of this, then we can go for the total discharge. So integration also need to be done from 0 to t, integration 0 to t. So integration 0 to 2 we can do. Now after integrating the dq, we'll get here q, and this part also you can write integration of that. This total part we need to be integrate this. So we can write 1 minus 1 by 2 mu del p by del x. These are the constant term I have taken outside. 1 by minus 1 by 2 mu del p by del x. Now integration of this ty, and yeah. So here you can write t square ty square, sorry, t constant term y dy, so ty square 2, and here y square is there, so y3 by 3, integration completed, and this is 0 to t. Now we can put the value in this upper limit and lower limit here, and again we can write this minus 1 by 2 mu del p by del x, bracket start. Here you can write tq, because t square tq by 2 minus this is tq by 3. Okay, or you can give just normal bracket, you can give square bracket not required. Anyway, this is the q term. So finally we can write q equal to, you can write minus 1 by 2 mu del p by del x, del p by del x into tq by 2 and 3 is the 6. So what we can write 6. So we can write here tq and 6 into 2, that is 12. So minus 1 by 12 mu del p by del x tq. So this is the discharge q. Now what do we need to find out? We need to find out, as we have discussed, u bar. So u bar equal to, I can write q by area A. So this is the q value, area we know that t into 1, okay, the thickness into the height t into the width, which is 1. So here finally what we'll get, what you're going to get, so t will be cancelled here, so that will be on behalf of q. This area is nothing but, we can write t into 1. Okay, so put this value in this, and finally again we are going to get here 1 minus 1 by 12 mu del p by del x, and this is t square. So this is another equation, we can just mark it, equation number 5. Now this is velocity average velocity. Now what is our intention? We need to find out the ratio maximum velocity to average velocity. So now we can find out by equating these two, by taking these two value, this one and the previous one, we can write u max by u average equal to just this value and this previous value, where it is, this one. This minus is going to be cancelled, t square, all these things is going to be cancelled. Only if you see here how much is there, 1 by 8 mu, there 12 mu is there, del p by del x, t square is there. Now let's see, del p by del x, t square is going to be cancelled, mu is going to be cancelled, so it is going to be 12 by 8. So 12 by 8 is nothing but this is 3 by 2. So I hope you understand. So this is the ratio, and this one again we can give a equation 6. So this is all about the ratio. Now again we need to find out one more thing is there, that is pressure drop. Pressure drop is there. So pressure drop, again we need to find out between two zones, either one side, like two different sections we need to consider, either This is one section, this is one section, and in these two different sections we need to find out the pressure drop. Okay, for the pressure drop, as I told, like means we need to here, let's draw like this. So this is section 1 and this is section 2. Okay, and the pressure is acting at this point P1 we can consider, and similarly at the second section, okay, there is a pressure will be there at this other end, like here. So here suppose P1 is there, and here I can write this is P2. Okay, so it's very simple. Last time also we have done the same thing. The same concept is going to be applied here. So because we need some sections to identify the pressure drop. At this zone what the pressure is there, and this zone what the pressure drop is there. Now for that again I need to consider the previous equation, what is here, equation 5. So let's consider this u bar equal to minus 1 by 12 mu del p by del x T square. So this one I can write here, the pressure gradient one side del P by del X equal to I can write minus 12 mu and u bar divided by T square. And now what we'll do, I'll just integrate this equation with respect to X. Okay, so let's integrate this equation with respect to X. Then what I am going to get, so integration of del P, so yeah, only del P will be there. So okay, keep one side, this one, and this one I can write in this way, u bar by T square, and here you can write dx, so that I can get it here. See this in dp, the change in pressure, we can after integration we can write in this way, like what is the pressure at this point and what is the pressure at this 2, and here what I'll get, this is the constant value minus 12 mu, and this is u bar. Now this is, we can write T square. Now delta this dx, integration to dx, again we can write x1 minus x2. Okay, this x1 value is nothing but the distance what we have taken. Okay, suppose this is the x1 is there and this is the x2 is there. Suppose I'm telling this value. Okay, now so here I can write again, just let me write, this is in terms of x2 minus x1, so minus will be there, minus plus can be written. So this is 12 mu u bar by T square, and here I can write x2 minus x1. So this is the pressure difference value P1 minus P2, and we know that x1 minus x2 equal to L I can write. Okay, now you can see where I'm giving the L, where I'm giving this x1 value. As I told you, this is the x1 value I can write here. Okay, and this is actually the total length is here also, you can consider x2, and length is that between these two sections, this is L, this is L. So L I can write what? L I can write x1 minus x2. So this value I can write in this way, P1 minus P2, P1 minus P2 equal to 12 mu u bar divided by T square into L, So this is the pressure difference, you can say, pressure difference in these two different sections. Now if suppose if HF is the pressure loss or the drop of pressure head, you can say that drop of pressure head, then also I can write HF equal to P1 minus P2 by rho g, P1 minus P2 by rho g, because these things already we have identified previously. So if HF is the drop of pressure head, then we can write HF equal to P1 minus P2 by rho g. Then what I can write this equation I can write finally P1 minus P2 by rho g equal to 12 mu u bar L by rho g t. Okay, this is the final equation. And in the previously, if you see in the during the circular pipe, we have got equation number 7. There we got d square. Okay, here it is L and T, and there it was I think 32. Here it is 12. So this is all about the velocity distribution. Now one more things I told you during this discussion, velocity distribution. I told you to, I'll tell you the shear stress distribution. The fourth is shear stress. I can just write shear tau distribution. This is another one. This is also very simple. Yeah, so here we know the formula, tau equal to mu into du by dy. So just we can write tau equal to this value, okay, mu into du. U value we just need to put the value here with respect to dy. That means minus 1 by 2 mu 1 by, where you got the value? Yeah, this one, minus 1 by 2 mu del p by del x t into 2y, t into 2y we got. So that equation we need to write. Yeah, so just put the value here, mu into del by del y, and here minus 1 by 2 mu, okay, del p by del x. Now t into y minus, this is y square, and this is bracket close. Okay, so this equation I just taken from here. There is u value. I just kept the value of u here. Now after this we can write tau equal to mu into minus 1 by 2 mu del p by del x, and this is t minus 2y, derivative of that. Just I have done the derivative here. And finally we can write tau equal to, I can write minus 1 by 2, mu is going to be cancelled, and this is del p by del x, and this is t minus 2y. This is the final equation, and this is equation number 8. So if this equation, if you see all these terms, minus 1 by 2 del p by del x, this all are constant along with the t also. And here the value you can see along with the y, the shear stress, and it is linear with the y value. So the shear stress distribution we need to consider. Now here I'll do this figure. The shear stress distribution should be like, you know, if this is the condition is there, then at this point it will be 0. So here it will be maximum, it will become like this. Okay, so this is the shear stress distribution will be there. And as I told you, the shear stress distribution is maximum when y equal to 0. When y equal to 0, the shear stress value is maximum, you can get here. And at the two different walls, this wall and this wall. So the shear stress is 0 when, now when y equal to t by 2, here shear stress is minimum. Okay, so this is the things. So we can write finally maximum shear stress tau naught. If you want to write, I can write minus 1 by 2 del p by del x into t. This is the final one. So this one we can give equation number 9. So I hope you understand this derivation, though it is a lengthy one, as I told you, because these are the equations we need to derive all these points, as I told. Okay, so how many things we have completed, you can see. One is shear stress distribution, Okay, and one is pressure distribution here, and ratio of maximum velocity to average velocity, and this is the velocity distribution. Okay, so I hope you understand this derivation. If you're having any kind of doubt regarding this or query regarding this, you can give a comment on the comment box. Thank you all.